Continuing our work with arithmetic sequences, we're looking now at a particular case, simple interest. You might have seen simple interest before, and it actually has its own, in financial maths it has its own formula. It's written in different ways. Sometimes it's written as I equals P times R times T over 100 if R is given as a percentage. Okay, there's different versions of that, but essentially that's what we got. And with simple interest, we have a starting amount and a finishing amount. The starting amount is often given the symbol A, kind of means the accumulated amount, and the other amount we given at the beginning is called the principal. It's the amount invested or borrowed. So to get the amount, we need to add on the interest we get from this step above, the simple interest, and we need to add that on to what we started with. So another way of writing that would be P plus PRT over 100. So that's financial maths. We're going to revisit that in a minute. Another thing you've studied, of course, is linear functions, y equals mx plus c. Why am I bringing up all these random bits of maths in a video that's supposed to be about arithmetic sequences? Well, we're going to try and link things together because that always improves our learning. So these things here are going to be linked with this here. Okay, so that's our goal. Let's suppose we have $100,000. Sounds good? $100,000. Let's say we're going to invest that at 5% interest, paid in a simple interest method, and it's 5% per annum is the rate. So simple interest means that at the end of each cycle, which in this case will be yearly, you get paid a certain amount of interest if it's an investment, and that amount is constant. So it's a constant addition. Now, maybe that's starting to trigger some links in your mind. A common difference, a constant increase. Okay, these ideas might be starting to trigger some links back to our work on arithmetic sequences. So let's see what we got if we want to work out the interest in each year. So the amount of interest is achieved by getting the $100,000 and timesing it by 5%. Now as a decimal that's 0.05 because I had to go 5%, which is 5 over 100, 5 per 100. And because it's 1 year, we basically times that by 1 and we get $5,000. So after 1 year, we have our balance is 100,000 plus 5,000, and that's $105,000. Let's now perform an investigation on this. So let's see what happens after a few more years. And remember, you can see that interest, well, you'll soon be able to see it if you can't see already, that interest added to 5,000 is constant throughout, because basically we've got 105,000 now, and so after 2 years we'd have the 105,000 plus another 5,000, and we have 110,000. It's going to write 110k to save some room there. $110,000. And that was 105, the previous balance, okay, plus the same yellow interest there. And again, that's constant, isn't it? So another way of writing that would be, it's basically the $100,000 that you start with plus 2 lots of 5k, $5,000. So next we've got 110,000 plus 5,000, because remember that is constant in simple interest, and we have $115,000. Okay, another way of writing that would be the original $100,000 plus 3 times that 5,000 in yellow. Alright, so there is a pattern emerging here. So for 4 years that number would change to a 4 there. Okay, and we'd keep adding 5,000 on. We'd add 5,000 on to 115,000 and it'd become 120. Alright, what about after n years? So being able to generalize in mathematics is huge. And what would it be? So after n years, which we might call a sub n, how do we get a value there? In this particular case, we've got $100,000 plus, if we have a look at these here, we replace those numbers there by n times 5,000, and that will get us any amount accumulated after a certain amount of time, any whole number amount we choose. Let's deconstruct this and try and make some meaning. So what we have here is the principal, that's n years, the number of years, and that is that amount of simple interest which we get by going P times R over 100. Each year we do that. So in general, using arithmetic progressions, we can work out the accumulated amount based on simple interest. This is not compound interest. This is simple. So P plus PRN over 100. Okay, where P is the principal, R is the interest rate, and N is the term number. The term number in an arithmetic progression, which corresponds with the number of years. Now this is provided that R is given as a percentage, okay, and the dividing by 100 of course converts that to a decimal for you. Earlier I was talking about some links, so let's link these things together. If we've got P, we can see that it's the same thing with the financial maths formula as with the formula using arithmetic sequences, so that's fine, and it's our starting value, and that corresponds with the constant C in a linear equation. We've got what would be called a independent variable here, and the variable here is time. Now, in this one it's the term number or the number of years. The rate of change is the gradient, and the rate of change in the financial formula is PR over 100, as it is here as well. So these things are linked ideas, and if you plot any of those, if you plot the inputs versus the outputs, you'll get a straight line graph. Now the thing with these arithmetic progressions here, they only operate on discrete values. So if you plotted that, you would just get a bunch of points which you would not connect with a line. With the financial maths or the linear functions, it's often discrete, so you can use values such as 10.6 years, okay, whereas that we don't go there with arithmetic progressions.